Welcome physics students. So in this video we're going to talk about the force of friction. And let me first give you a bit of a warning. There's a lot of concepts to the force of friction. The calculations are no more difficult than the force of gravity that we studied in the last video. But friction is complicated. First of all, there are two kinds of friction and a lot of different things can happen with friction. So we need to really work on the concepts. A lot of trick questions you could make with the force of friction. So that being said, let's move on. So remember, as I said in the gravity video, that we're going to be in the remainder of this force topic studying forces that are consistent and predictable, meaning we could write a formula for them. When it comes to people and animals, the forces are not always consistent. But when it comes to things like friction, if the conditions are the same as they were yesterday, the force of friction will be the same as it was yesterday. Always the same, so that means we're going to have a formula for it. Okay, so to introduce us to the concepts, the many concepts behind friction, I've got here a wooden block with some weights on top, some masses, on a wooden board. And what I'm going to do is pull it over here with an increasing force. So, if I pull on this block with 1 Newton, what do you suppose the force of friction is? Is it exactly 1 Newton, like my 1 Newton? Or is it more than 1 Newton, or less than 1 Newton in the opposite direction? A lot of people will hypothesize that it's more than 1 Newton. And their reasoning might be something that, like, look, it's holding me back, so it's got to be stronger than my 1 Newton. But it's not true. It's exactly 1 Newton. If it were, for example, 1.5 newtons against my 1 Newton, this block would have a net force of 0.5. And think, if I am pulling 1 Newton here and some person is pulling 1.5 that way, isn't the block going to move that way? Of course, right? So friction is not more than I'm pulling, because if it were, imagine pulling on a block like this, you pull like this and then it starts dragging you forward. No, it doesn't do that. It mirrors what you do. So for example, if I pull 2 newtons, friction is also 2. If I pull 3, friction is 3. Okay, so however hard I pull, it matches it. But of course, obviously there's a limit. Like, for example, I can't hook a bulldozer to this, a giant machine taller than this room, and it pulls on this block with 1,000,000 newtons, and then the block pulls 1,000,000 back and it doesn't move? No, of course, the block would start to move. So there's a limit to how long it'll match you for. So for example, I pull 3 newtons, friction's 3. I pull 4, friction is 4. Okay. I pull 5, friction is 5. I pull 6, friction is 6. I pull 7, friction is 7, 8, and 8. And then it starts sliding, and notice what happened is the needle dropped to about 7. So I got to about 8.5, let's say 8, and now it's 7 as I'm sliding. So that means there are actually 2 kinds of friction. One keeping something from slipping, and one while it is slipping. And they're different values. Okay, so that's my first point. Let me move the block out of the way and the board out of the way temporarily. These notes will basically summarize what we saw with a little demonstration. So I'll pause the video here to allow you to copy these notes down. Okay, so here's a little diagram of what I was doing. I was pulling on a block with an ever-increasing force. This graph shows what happened. If I pulled 1 Newton, for example, I come up here and I go over and I see that friction was exactly 1. If I pull 2, I go up to the graph, I go over, friction was 2. So this has a slope of 1. We call that point where there's no slipping static friction. I'll define them later in more detail. Static friction, okay? So that, of course, continues until I get to a limit. Maybe it's 8 newtons then at 8 newtons, friction is 8, but if I try and pull 9, I can pull 9, all right? So I pulled 9, but the force of friction dropped to 5.5 while it slid. And no matter how hard I pull, if I keep increasing this applied force, friction kinetic, the sliding friction, will always remain 5.5. I could pull 1 million newtons, as hard as I can, and that wood block will fly across the board, and the friction sliding will still be 5.5, just like when I dragged it ever so slowly. Okay? So, let's summarize in words. Static friction, the force parallel to a pair of touching surfaces. So, a couple points. First of all, you need 2 surfaces for friction. I'm trying to rub my hand on something, right? I'm not getting any friction, right? I need my other hand, and now I've got 2 surfaces friction. Or I could take my one hand and rub the whiteboard, or rub a piece of wood, right? So you need 2 surfaces, a hand, something else, or shoe and floor, right? So you need a pair of surfaces that are touching. And it's the force parallel. Remember, in the last video, we learned the normal force was the surface preventing something from breaking through it. So it pushes perpendicular to support something. That's normal force. Now if I pull like this, friction is the opposite way, parallel to the surface, not normal or perpendicular, parallel to the surface. Okay? And static prevents them from sliding past each other. The surfaces are rooted together. It exactly matches the applied force up to a limit. And I'll talk more about this in a minute. I'll just, mention it briefly. The objects can be moving. You say, wait a minute, I thought they weren't sliding past each other. Well, rolling tires, I'll talk more about that. Those are static friction. Kinetic friction, the force parallel to a pair of touching surfaces generated as the surfaces slide past each other. It's constant or independent of the applied force or the speed, and the object can be at rest. People say kinetic, oh, it's moving. No, you can have something at rest and there's kinetic friction involved. And that's the tire burnout. So let me talk a little bit about tires, because this is actually important in everyday life. What I'm going to say, the knowledge behind the friction concepts could kill people if they don't understand it, okay? First thing, in your car, you never want to create kinetic friction. Well, I suppose you want to do it if you're showing off and you want to burn out your tires, right? But for safety's sake, you don't, or even from a performance standpoint, you don't want kinetic friction because it's always less than what the static can be. So if you hear your tires squealing when you're driving, think amateur right away. Because a professional race car driver understands this and never makes the tires squeal, never makes kinetic friction. How is it that when you're going down the road without squealing tires, it's static friction? Well, here is a round object. Let's say it's a tire, right? So look at this point. I'll put my finger right here on the tire. As the tire rolls, it comes down to the road surface and touches it briefly. And then when the tire continues to roll, it lifts back up. So a rolling tire is a brief touching of the rubber to the road and then a lifting. But a continuous, because the tire is round. So it's static friction as the tire is rolling down the road. When you go around a corner, you get friction from the tire. And if it's not squealing, it's static friction. When you press your gas pedal to speed you up and you don't burn out, static friction. And when you hit your brake to slow down and you don't squeal the tires, static friction. Tire burnout, I can have the tire at rest, floor the gas pedal, and the tire spins out, and it's not moving anywhere, right? It's just spinning. And you see that at the point of contact, we have rubbing, sliding. So that's kinetic friction, okay? Now, as I said, professional race car drivers, if you watch them, they don't squeal the tires. They know whether they're speeding up, slowing down, or turning. They want to get the tire almost to the point of sliding, but not to the limit, not past the limit, because then they skid and they either crash, or if they're taking off and they spin out, their opponent doesn't spin out and takes off with more friction in the tire, takes off and wins the race. Okay? So they know through training, because they're professionals, how to keep the tires near here. Okay? Maximum performance. Of course, the average driver is not a professional. And so what that might mean is you come around to a corner going too fast and you demand too much of your tires and they start slipping and you go off the road and crash into a guardrail, right? Obviously not a good thing. Or a case where maybe you're safe, you're self-conscious, you're a good driver, you don't race around. You can still, in a situation, panic when something comes out in front of you and you jam on the brakes as hard as you can. Most people, like let's suppose you're going 60 miles down the road, miles an hour, and the tractor trailer pulls in front of you. You hit that thing, you're in big trouble, right? So people jam the brake as hard as they can with all their leg muscle. They squeeze on that brake because they want to stop. They don't want to, have a fatality, right? So in old cars before they invented anti-lock brakes, what would happen is the wheels would lock up because you press on the brakes so hard, the brakes close so tight and the tires stop turning, you skid, and now you're going to crash. Now, a professional race car driver would hear the screeching tires as he's going toward something about to crash and let go of the brake. How many people would have that self-awareness to let the brake off, to allow the tires to spin? How many people would think, oh geez, I see the tractor trailer, I'm about to crash. I learned in physics class that kinetic friction is not as effective. Let me let off the brake and let the wheels turn so I could get static friction again. Okay, right, nobody's going to think that. They're going to press even harder because we're not professionals. So engineers have learned that that's what happens. And so they invented something called anti-lock brakes. What happens now is when someone jams on the brake and the tires, if they're about to skid or if they start skidding slightly, there's a computer that detects that the wheels are not turning anymore. And a computer is good at this because they don't get scared, right? So a computer could say all that brute logic and let go of the brake. You're squeezing on it as hard as you can. But the computer lets the brake go and lets the wheels start spinning. Okay, not for long, like 1,000th of a second or something. And then right when the wheel starts spinning, it reapplies the brake. So it keeps the tire with software here while you're slowing down so you get the maximum braking and you don't crash. So that's anti-lock brakes to keep your tires at static even when you panic, okay? So just a little something. Kind of got off topic in a sense, but I always like to talk about tires and skidding because students should know you always want to stay here, okay? Professional race car drivers, they do stay here, okay? But you should know that you should too. All right, so now, what about a formula? Well, let's suppose we do a little experiment. And what I'm going to do is I'm going to, first of all, ask you, what are the ways that I could maybe make more friction? In other words, make it harder to slide this, okay? Now, think about that for a second. Maybe you said, stack more blocks on here. And that would make it harder to drag. Somebody stands on it, now it's even harder, right? And that's correct. Technically, what we're doing is we are increasing the normal force between the surfaces, and that increases the force of friction, okay? Or I could decrease the normal force, that decreases the friction. So normal force, that's one thing. there's a second thing. What else could I do to maybe make this easier to slide? Well, maybe some of you said, squirt a little oil here. Yeah, so I could take it off wood and put it on some ice. Okay, now easier. Or I could put it on rubber. Now it's harder. So, normal force is one thing. Surfaces is the other thing. Okay, those are the two big factors that affect friction. So my experiment's going to be to see how the normal force affects this friction situation. So what I'm going to do is make a column with normal force. And then, now I need two columns. Force of friction, I'll put FF first of all, force of friction, static in newtons. Remember, that's the limit that it takes to get something to slide. And I'll do force of friction, kinetic in newtons. How much to keep it sliding? So first of all, if I have 0 newtons of normal force, I would have 0 friction. All right, so imagine, how do you get 0 newtons of normal force? Maybe I take this to outer space and I put this on the block here, on the board, which really, they'd both be just floating there, right? Board floating, block floating, and then I could just barely nudge this and it'd kind of sail across with no friction. So if you don't have anything pulling this down into the surface, you're not going to have any friction. Let's suppose I put 1 newton in normal force, and then I find that it takes 0.8 newtons before the thing starts sliding, and then only 0.6 newtons to keep it sliding. Then I add another block on top of the wooden block, so I increase the normal force to 2 newtons. Right? There's now more weight and therefore more normal force. What I would find is now it would be harder to get this thing to slide. And doubling the normal force in an experiment, you would see that the force to get it sliding doubles, and then once it starts sliding, to keep it sliding, the force also doubles. 3 newtons, now I've tripled the normal force. I would triple the force to get it moving and triple the amount to keep it moving. And so on and so forth. Quadruple, now it would take even more force to get it moving and even more to keep it sliding. Okay, so now we're going to graph that. I'll pause the video to give you a chance to copy it down our little data table. Okay, so okay, friction experiment. So if I plot 1 newton in 0.8, 2 in 1.6, 3 in 2.4, these you see grow both in a linear pattern. We say the variables are proportional to each other. So I might plot those like this. And then I could do a best fit line. Right? And so I've completed that data plot. Now I'm going to plot this and this data. So this, plot those points, and notice the second set of points, they also begin at 0, 0, but they're always a little bit lower. Oops. but there's still a linear pattern. I could draw a best fit line through these points. So this would be the static data. And this would be the kinetic data. Now, don't write this down, but remember in math class, you could write the equation of a straight line like this. Okay? Y equals mx plus b. And if you see, both these lines go through the origin, so there's no y-intercept. So the formula is really y equals slope times x. But what do we have on the y-axis is force of friction. Okay, what do we have on the x-axis? We have the normal force. Now, the slope, we use a special symbol in the case of force of friction. The slope of this line, we use a Greek letter from the Greek alphabet. It's called mu. Okay? If you want to know how to write this, it's like writing a U, and you know how a U, you then put this little down curved line over here. You put another one on the other side. Okay? Or you could do it in one shot like this. Okay? Mu. Okay? So, this is the equation for force of friction. But what is this mu? Okay? It is called the coefficient of friction. So that's what it's called. And what it is the bigger the slope is, the more friction you have. So it is a measure of how sticky two surfaces are with respect to each other. So let me jot that down. Okay, so I'll pause the video to give you a chance to catch up with the notes. Okay, so coefficient of friction, measure of how sticky two surfaces are with respect to each other. There's a different mu for each pair of surfaces. Rubber shoes on a wooden floor like at a basketball game, there's a particular coefficient for that. The coefficient doesn't matter who's standing in the shoes. You could have a little kid standing in the shoes or a giant 7-foot tall basketball player. The coefficient for rubber on wood is always the same. Okay? You might get more friction because you have more normal force, a taller, bigger player standing, creating more normal force. So that gets more friction than the little kid who has a small normal force and the same coefficient gets less friction. Okay, so normal force effects and the surfaces. So then you take that basketball player and they're on the wood floor and then they go out into the parking lot, which is made of concrete. Rubber on concrete, new coefficient. Rubber then on asphalt, blacktop, a different coefficient. Okay, every pair of surfaces, there's infinite coefficients of friction. Now, in the Regents curriculum, they just focus on a few. Remember I said we've got this reference table, so I'll come closer to the camera, okay? And front cover, back cover is what we're going to be using for almost half the year. First of all, the force of friction equation that I wrote down is right here, right where my index finger is. Force of friction is mu F normal right there. Okay, so again, you don't have to memorize that. The front cover has some, at the front cover at the bottom right, you have approximate coefficients of friction. You have some surfaces. Rubber on concrete, 0.68 and 0.9. So this is the static value, the friction to just to the point where the surfaces are going to slide. This is when they're sliding, you plug in that value. Notice rubber on concrete wet, slightly less. Wet roads are more slippery. That's why they say you should drive slower. We got rubber on asphalt dry and wet. Rubber on ice, waxed skis on snow, very small coefficients because that's a slippery situation. Wood on wood, we got two coefficients, steel on steel, copper on steel, and Teflon on Teflon. So for those pairs of surfaces, you could go to the front cover. Okay, maybe I will do one example problem. Well, let's do 100 kilogram wood box. Okay, so there's the example. So first thing, remember I erased the formula. Friction is coefficient times normal force. We need the normal force. And with a 100 kilogram box, the normal force is in 100. What we first have to do is calculate the force of gravity, okay, which will then be the normal force. So force of gravity is mg. Oh, actually, let me do Fg equals normal force. And this formula is on the reference table as well. And so what we get is 980 newtons of normal force. Now, to get the force, to get it to slide, that's the force of friction, static. And the formula is coefficient times normal force. So I got this formula off the reference table. Of course, it didn't have the S there. I put that just to, for me to realize I'm calculating the static limit. And I look up on the front cover of the reference table for wood on wood, okay, right here, okay. And what I want to get the box to slide, I want the static value, which is 0.42 right there. Wood on wood static 0.42. So I plug that in for coefficient. And I get a calculator out. And I could say 980 times 0.42, enter, and I get 412 newtons. So that's how much you have to pull on this 100 kilogram box to break it free and start it moving. How about to keep it moving? That's the kinetic value. Same formula. The only difference now is that instead of using Oh, let's get the focus. So wood on wood, instead of using the static value, I'm going to use the kinetic value right here, okay, which is 0.3. So 0.3 times 980 newtons normal force. 980 times 0.3, enter, 294. Less to keep it sliding than to get it sliding. All right, let me pause to give you a moment to jot this down. Okay, so now let me just mention one thing. Like I said, friction has a lot of concepts and it's very easy to make a trick question. I could say a man pulls 250 newtons and then the rest of the problem. And then I say determine what the force of friction is for that wooden box. And people say, oh, 250 newtons. Okay, so let's see. They calculate the force of friction static and they say, oh, it's 412. And the man's not pulling more than 412, so it's not kinetic, so friction's 412. And they calculate, they report this answer. Not correct. The man pulling 250, not greater than this, friction is exactly 250. Not this answer. So you calculate this only to see that he hasn't exceeded the limit. He's under the limit at 250. So friction is actually 250 newtons. See how that could be like a really bad trick question? So, all right, so that's it for today. The force of friction, probably the most complicated force that we're going to learn about in this topic. Remember, there are two friction values, two types of friction: static when there's no slipping, kinetic when there is slipping. Static can be more than kinetic. It might not be if you're just pulling very lightly. And then there's a formula, coefficient times normal force. Very often you get this on the reference table. It's just a constant for a given pair of surfaces. This is the normal force between the surfaces, and you calculate. So that's it for today. I'll see you in the next physics video.